Hello. Today I want to talk about pattern matching and the use of pattern matching about the COVID and the genome of SARS-2 COVID. Very quickly, this is topics that are known for most of you. Therefore, if you want to see more details, if you are not completely familiar with this concept, you can view this video in slow motion. We consider a finite alphabet, for example, a binary alphabet, and we define a factor of the alphabet as a set of consecutive symbols. The pattern matching is given two sequences, a short one, W, and a longer one, X. It is to determine if W is a factor of X, on how many times it appears in X. It has several applications, parsing, compilation, search, compression, and so forth. You can imagine around the pattern matching problem probabilistic models on sequence in order to infer how performant are the algorithm, what is the expectation of the performance. The simplest of those models is the memoryless model, when the probability of a sequence the product of the symbol. It means that each symbol occurs independently of the previous and the next symbol. Here are some notation. The length of the sequence, the number of currents x sub w, the number of currents of w in x, and it is relatively easy to get the average number of currents of w in x is this quantity. When x is relatively large compared to the length of w, then the number of expectation is basically the length of x times the individual probability of w. All this result can be extended with a little more complicated shape for Markov sequence generation with finite memory. Here is a word sequence matching problem. Imagine a sequence of different words, W1, W2, WK, K words, and text X. And we want to check the following property. If the factors WI appear in this order in X, we denote X sequence W1, WK, the number of such occurrences X. We have the expression for this average number. And when the cumulated length of the factors is negligible compared to the length of X, then we have the expectation of number of occurrences as being the length of X to power K divided factorial K times the individual probabilities of the factors. If the order is indifferent, it means you have to multiply by factorial K, we get this expression. So you keep this in mind. It will be used in the next part of the talk. What is very useful for the pattern matching problem is the suffix and prefix trees. This is a very useful data structure. It is a tree where you store all suffixes or prefix. It is equivalent, it is the reverse. And this is a very convenient structure because the longest copy of a factor, of a prefix of factor, is found by exploration of the tree of suffix tree of X. The computation of the suffix tree, we have several ways. There's a naive algorithm, since it is a trie, it is in x log of x. But since it is a suffix as a unique sequence, there is a Rissanen algorithm, which makes it in linear time. the search in the tree is in the log of x, the height of the tree, basically. The joint complexity. So we are going to use the joint complexity. The definition of the joint complexity is basically it's the number of common factor between two texts. Assume that the texts are x1 and x2. Then you see the common factors, and the number of common factors is 25. It is very easy to compute. It is linear, but via suffix 3 superposition. You just have as a gate superposition suffix 3 and look at the common branch and count the common nodes. And it's very convenient to detect when two texts are very close or have a lot of similarities. And what is interesting, it is you can use it for real-time classification of tweets or social media trend propagation, because it is agnostic of language. You can use it in any language, and more importantly, it is resilient to misspelling. If you make a typo, the joint complexity will just jump above the typos, and you will still detect the similarity. The theoretical performance of joint complexity, this has been analyzed before, when the text x and y are the same length, but built from sources with different parameters, then the joint complexity is sublinear in the length of the text. And the more sublinear it is, the more different are the sources. Now a new result is when the texts are of different length, but from source with same parameters, then the joint complexity is linear with the length of f kind of linear, with this expression, which looks like an entropy. And of course, if you want to have this is a self-promotion part, if you want to have more details on the result and algorithm, you can look at the beautiful paper, the book written by Wojtek and me, and also this paper about the use of joint complexity and social networks. But now, as you can see, the title of the book is From DNA to Twitter. In fact, the first application of pattern matching was on genome. And here, I don't know if you recognize this sequence, but since there is a title of the talk which gives an indication, this is the coronavirus SARS-2 sequence, this evil thing. So let's play with this sequence, and here it is some of the result I obtained by playing joint complexity and SARS-2 genomic sequence. First, I compare the SARS-2 genomic sequence with the first known bat coronavirus, with respect to be the common ancestor, bat alpha coronavirus, which has been discovered in 2007. And in this figure, this is joint complexity, cumulated joint complexity, passed from right to left between the SARS-2 sequence and the bat alpha coronavirus sequence. I made it from right to left for convenience of the computation, because I built the suffix 3 from the right to left, therefore was more convenient to do this from right to left. And in dash, this is what will be the joint complexity if the sequence were purely random, uniform. So as you can see, that the sequence, the BAT alpha coronavirus sequence, has some similarity with the SARS-2 sequence. This is a confirmation that they are related. Now, this is the same picture, but instead of looking at the accumulated, we just normalize with what will be the average with random sequence. And I add on this plot the genome complexity with the HIV genome. So you can see something which looks surprising, but it is possible because the sequences are not random, that the SARS-CoV-2 is related to the BAT alpha, the BAT coronavirus, but it is subcorrelated with the sequence of the HIV. They are not related. Basically, the gene complexity is less than what will be expected between two purely random sequences. So, although they are not related, Perez and Montagnier have discovered that there was accidental insertion of HIV factors in the SARS-2 genome. Here, there is a paper where there is the localization of all these 19 factors, which are of length 20, so very short compared to the length of the genome, which is over 30,000. And in this picture, I just look at the maximum of matching between the sequence, but expressed in standard deviation unit. So we see that you can reach more than 15 standard deviation unit, which is considerable, and therefore this insertion looked very accidental. Indeed, if you consider this as a set of fixed factors, then the probability of such accidental insertion, if you remember the slides about the word sequence problem, will be order 10 to minus 144, which is basically, if you want to get such result, you should better bet on lottery. Therefore, the conclusion of Perez Montagnier that this the SARS-2 COVID virus has been forged, has a confirmation that of the accidental insertion that in this picture I plot the same maximum gene complexity discrepancy, but when I consider the reverse of the sequence of SARS-2 COVID, in this case all the accidents disappear. Montagnier is a Nobel Prize who discovered the HIV genome sequence, so maybe the reason why he was interested to do the comparison. However, this conclusion was a little too fast because we can assume. Basically, the people look at the matching and they discovered that basically they were not in important places. They were not very short, not in important place, and let's assume that you unfix a matching factor and assume that basically some people decided to use all the corpus of about HIV sequence. It's probably of around 1 million base. Because in the matching you can find many sequence about simian IV, sequence about human IV, IV1, IV2, and also the reverse sequence for strange reason. In this case, if you don't fix the matching factors, then the probability, the average number of matching of the corpus is m times n being the length of the SARS-2 genome, times the probability of matching. If the probability of matching is 4 to minus 20, basically because the factors are left 20. Then the probability of K matching using Chebyshev is of this order 1.410 to minus 3. And if you multiply by a tolerance of maximum of 3 errors, basically you get a probability to have 19 matching less than 1.6. Therefore, it is less accidental than it was looking before. Therefore, I call this weak pattern matching because if you unfix the factors, it's not unlikely to get 19 such matching. In fact, this will not be true if you consider that the matching sequence are independent. But in fact, they are not independent because they are all coming from HIV. In this slide, you can look how the matchers can match between them. Therefore, to be the proof that they are not that independent. And this is what you obtain when you take segment 11 versus the other segment. You get a similar accident. And but we cannot claim that it has been forged because this data are from 1993 and the technology for engineering DNA was not existing at that time. Here we are going to look at strong pattern matching, and recently there has been bad coronavirus claim has been very closely related to SARS-CoV-2, and indeed when you do the slides and complexity you can detect the part which are common. In fact, it is the bad coronavirus, the new bad coronavirus, we know only 2 segments, and these 2 segments match very well, and it has been discovered in November 2020. In fact, we can say that it matches maybe little too well because we arrived to normalize strong pattern matching of order 40, which is kind of excessive. Now, if we go a little back in the past, we have in 2013 bad coronavirus called rat G93, and it has been discovered 6 years after bat alpha, but in fact it shows low matching with the bat alpha, but very strong matching with the SARS-2 COVID, which has been discovered 6 years later. Here the cumulative normalized drug concentration is 20, order 25, and we can see that the 2 genome match very well on the whole sequence. Extremely well. In fact, we can use joint complexity to detect since they are matching so well, so that sometimes there are substitution, but sometimes there are insertion or deletion. And joint complexity can detect when there are just substitution or when there are insertion. And here, to do that, you use instead of enumerating the common factor, you just detect the largest common factor, and the relative position gives you the offset between the sequence, and this is basically the actual figure of the offset obtained by comparing the largest common factor. And when the offset increase, there is an insertion. Therefore, from the rat G93 to SARS-CoV, there has been the insertion of 20 base where you can exactly spot. When there is a decrement, which is not the case, then it means it is a deletion. So this closes my my talk. Thank you for listening, and don't forget that the coronavirus is still a strong bad thing and it's still mutating. Be careful. Thank you.